Welcome to the third and final part of Scanning Thermal Microscopy Basics. In this part of the presentation, you will learn about lock-in techniques, other ways to improve resolution, different variations and various applications of scanning thermal microscopy, and will conclude with a brief history. This presentation has been brought to you by PicoCal and has been written by Amar Basu and Angelo Gaitis. As indicated earlier, one way to reduce the thermal noise associated with scanning thermal microscopy measurements is to reduce the measurement bandwidth, and that's reducing the delta F that we saw in the equation earlier. To do this, we have to basically reduce the measurement bandwidth, and this can be done using a lock-in amplifier. The approach is to sinusoidally vary the probe temperature, and this is typically done at less than 500 Hertz. And the change in probe resistance will be monitored at a harmonic frequency. Let's take a closer look at this. A lock-in amplifier is included into the system, and the lock-in amplifier provides a sinusoidal excitation into the readout circuitry. If the excitation occurs at some frequency, then the power going to the probe is going to occur at double that frequency, because the excitation signal is a voltage, and the power going into the probe is proportional to that voltage squared. This results in a modulation of the temperature of the probe and a modulation in the tip-sample interaction signal. This signal is sensed by the lock-in amplifier. If we look at the frequency plot of what is going on, again, the probe is excited with the voltage at frequency omega. Since the power going into the probe is proportional to the voltage squared, the probe heating occurs at a frequency of 2 omega. And the signal, which is sensed by the lock-in amplifier in the circuit, this signal represents the probe-sample interaction. These signals are both at 2 omega and at 3 omega. By monitoring those two signals, we can gather different information about the thermal interaction between the tip and the sample. By using lock-in techniques, we can improve the thermal resolution by up to 2 orders of magnitude, and in some cases more. Other ways to improve the resolution. The fundamental limit for thermal microscopy is Kt, where K is a Boltzmann constant and T is the temperature. At room temperature, this value would be equal to 10 to the negative 21 joules, which is a very, very small amount of energy. Typically, under regular scanning conditions, the noise limit is much, much greater than that. In order to improve resolution, we can scan in vacuum conditions and we can protect from light. Scanning in vacuum reduces a lot of the parasitic heat flows which occur through the gas or through the liquid meniscus near the tip. And it also reduces a lot of the Brownian noise which may occur. Protecting the system from light will prevent the probe from heating up. Often these probes have a very high thermal resistance, and even shining a little bit of light on it can cause a difference in temperature shift in the probe. It's very important to keep the probe system away from light in these cases. A very important way to improve the resolution is through the design of the probe. Microfabricated probes offer small tips for high spatial resolution. They also offer very high thermal isolation, which increases the sensitivity of the scan. Most importantly, the small thermal mass of the probes allows them to be modulated at up to 500 Hertz for doing lock-in type measurements. And incidentally, it also avoids the low frequency or 1 over F noise, which plagues many types of measurement systems. There are a number of variants to scanning thermal microscopy, which we won't go into the detail of, but it's worth mentioning. Thermal profilometry is a system where the temperature signal is used to control the z-axis height of the probe, similar to the AFM technique. This mode makes temperature and structural correlations possible. Optical absorption spectroscopy is used to identify chemical species with a nanometer resolution and also to determine the spectral absorption of various materials. Contact potential maps can be used to measure the contact potential between the metal tip and the metal on the sample. It can be used for measuring thermal conductivity as well as electrical properties of the sample. There are many applications of scanning thermal microscopy today. One of the major ones is defect and hotspot detection in semiconductor manufacturing. Another interesting use of scanning thermal microscopy is in subsurface imaging. Atomic force microscopy can only detect features at the surface of the material, but scanning thermal microscopy can actually detect subsurface features which change the thermal conductivity of the tip-sample interaction. From a purely research standpoint, SThM can be used to study thermal and charge transport at sub-100 nanometer length scales. And from a pharmaceutical and biotechnology standpoint, SThM is very useful in the thermodynamic characterization of material properties such as conductance, specific heat, glass transition, and melting temperature. These types of measurements, if they can be done with very high spatial resolution, is of immense importance to material scientists, pharmaceutical compound development, and biomolecular analysis. We'll end with just a little bit of a history of scanning thermal microscopy, just for some perspective. In 1986, the atomic force microscope was developed by Binnig et al. In 1992, saw the development of scanning thermal microscopy for contact potential measurements. This was the first application of scanning thermal microscopy, and it was developed by Nanemacher and Wickramasinghe. In 1993, Majumdar developed scanning thermal microscopy with force feedback. 1994 saw the development of the Wollaston wire probe, which was essentially the precursor to the microbolometer probe. From 1995 to 97, the first microfabricated probes were developed, and these were thermocouple probes developed by Davis and Luo. The Wollaston wire probes, which were developed in 1994, were first used for calorimetry by Hamachi and Pollack in 1996. In 2000 to 2007, saw a lot of research in the area of microfabricated bolometer probes and probe arrays as well. This work was done by a combination of researchers which included Wendeman, Majumdar, Gyanchandani, and King. With that, we'd like to thank you for your time. Please visit PicoCal at www.picocal.com or email us at info@picocal.com for more information about scanning thermal microscopy and our products. Thank you again for your attention.